In this video, we're going to extend the linear regression to high-dimensional problems in order to find regression surfaces that are given by hyperplanes. This will result in the linear least squares loss in a matrix form, as you can see on the right. Let's get started. Hi and welcome to this new video. We will again look at linear regression, an extremely powerful algorithm for machine learning. Let's look at our agenda. I first want to introduce to you the directed graphical model for this high-dimensional case. Then we will derive the least squares loss with a univariate normal. We can then modify this least squares loss to arrive in a matrix form, but we can also equally derive the matrix form by using a multivariate normal distribution. And then finally, we will look at a demo in Python. Okay, then let's start with the directed graphical model. For this, I want to look again at this visualization here. So in contrast to the one-dimensional regression, we now have two input axes that are indicated here. So this is called X and Y in this particular case. And then we have a third axis Z, which is going to be the dependent axis. And then we are given a couple of points. These are indicated by the blue scatters. And we are asked to find a surface, a hyperplane, which approximately fits in these points. We can translate this as following. So we will start first with our given nodes. And in this particular case, those are our xi's. And these xi's are not coined probabilistic here because we are just looking at them as some given points in this two-dimensional input space. But in contrast to the one-dimensional linear regression, these are now vectors, so I will give them this underscore here. Theoretically, you could of course also make them probabilistic, for instance by using a deterministic distribution. And these xi will then cause yi's. And these yi's are our dependent coordinate, and these one again are one-dimensional, scalar valued, and these are also given, and they are probabilistic. And then of these xi, yi pairs, we have n of those, so let me use plate notation. And then similar to the one-dimensional aspect, we have to define the probability distribution for our yi's. And in case of our ordinary least squares problems that we are looking at here, this is a normal distribution. So we will say that yi is going to be distributed according to a normal. We will look at the details in a second. And this normal distribution has two parameters. So we will have a mean and a variance. And now we have to be a little bit careful because yi is a scalar valued quantity. So we will just have a univariate normal distribution here. And this univariate normal takes a variance or a standard deviation. And here in our case, we assume this one to be given. So this one is our sigma. But then we also need the mu. And the idea, again, similar to the one-dimensional linear regression is that the mean of our normal distribution is dependent on x. So we have to find a way in order to contract our x into a scalar, and this can be done by a scalar product with xi and a parameter vector m. And this one is our primary unknown for the linear regression problem. So these are the weights or parameters of our machine learning model. If we then want to write this down, we could say that yi is going to be distributed according to a normal distribution over yi, with mu being given as xi transpose m. So a scalar product between the coordinate vector xi and the parameter vector m, and then the sigma, the standard deviation / variance that we are given. And graphically, you could think of it as following, that given a particular point in our two-dimensional input space, so let's say for instance this point here, we will have a corresponding position on our hyperplane, and at this position on our hyperplane, I hope I can draw this properly, we will have a normal distribution, maybe something like this, and this normal distribution is alongside the z-axis. And by this we define that we have a spread of our variables alongside this z-axis, but the mean will always be on the hyperplane. And we can pick out another point, so maybe this one here. this would then correspond to approximately here on our hyperplane, we will have the same normal, so the same normal distribution in terms of the standard deviation or variance, but its mean position is slightly changed. And you can see that here. So maybe approximately this one is at z equals 0.7, and this one approximately might be at z equals 0.3. And these set positions, or the mu positions of our normal distributions, are given by the scalar product of our coordinates. And here in this particular case, they consist of a two-dimensional vector and a two-dimensional parameter vector, which we want to find in our optimization problem. Of course, we could also use a directed graphical model, which uses a plate notation for the input dimension. Just for the completion, I want to do this here. So let me say this is equally to the following. So we will again have our n plate for the n data points that we have. And then we have another plate in here, which is the d plate. And inside the d plate, we have our x coordinate, or our x point of the data that we have. And maybe we can use x comma d here, xi comma d here. And then our yi point will stay the same. So here we will have our yi, and then this yi, or maybe let me first draw the arrow here. So the yi is caused by the xi comma d, and then the yi takes, of course, our sigma again, and that is here. So this is our sigma, and then we have another plate notation up here. So let me put that here. So this is another d plate, and here we will then have our unknown md. So because m will be a d-dimensional vector, and every data point, so every xi is going to be a d-dimensional vector, and this d can be any dimension. It can be 2, but it can also be 1,000, 1,000,000, you name it. Okay, both ways are equally valid to represent our linear regression in high dimensions. So let's use the definition of the probability of yi as a normal distribution, with the mu being dependent on the xi position, in order to properly write down its probability. So we will get the following, that the probability of observing the yi point given xi, vector, and m and sigma is going to be first our normalization, so 1 over square root of 2 pi sigma squared, and then multiplied with the exponential of minus 1 over 2 sigma squared, and then we have yi minus xi transpose m in brackets squared. And again, let me highlight that this one here is a scalar valued quantity. So this one is our mu, and it is scalar valued. So the distribution over yi, or one data point, or in other words, the dependent variable for one data point, is univariate. And this is done by contracting down the dimension of our input to a scalar by the help of a scalar product. And then we can use this probability in order to define our likelihood. So let me define the likelihood. And the likelihood of our data is going to be the product, or given an IID assumption, is the product of all our data points, so from I0 to capital N-1, over the probability that our yi is the ith observation, and xi is going to be the ith observation of x as well. So again, we have a vector here, and then we have our m and sigma. And if we then plug in our normal distribution, so we have the product from I0 to N-1, and then we have our normalization constant, so 1 over 2 pi sigma squared times the exponential of minus 1 over 2 sigma squared, and then lowercase yi minus lowercase xi transpose times m in brackets squared, and then closing brackets for this exponential. Then let's look at our directed graphical model again. So if we scroll up, we see that the only unknown or thing that we want to find here in our model is the m value, so the values of the parameters or the values of the weights in our linear regression. In other words, this also means that in our assumption, the sigma is given or known and not of interest. And since the sigma appears in our prefactor, we can kind of ignore that by looking in terms of the proportional and then moving the product over to the exponential. So in other words, we're getting this is proportional to the product from I0 to capital N minus 1 over the exponential of minus 1 over 2 sigma squared, lowercase yi minus lowercase xi transpose times m in brackets squared and then closing brackets again. And this is the usual problem that you will find in maximum likelihood estimates of the normal distribution, that if we have a product over exponential terms, and this kind of allows us to move the product into the exponential by converting it into a sum. It's because if we multiply multiple exponentials that all have the same basis, so here they have the basis e, then we can add up their exponents. So this one is going to be equal. It will still be proportional to the likelihood. And here it is equal then to the exponential of minus, and then this will always be a constant prefactor. So minus 1 over 2 sigma squared. And then here we will have a summation from I0 to capital N minus 1 over lowercase yi minus lowercase xi transpose times m in brackets squared and then closing brackets. And the reason, of course, we're doing this proportional here is that in the long term, we're going to perform a maximum likelihood estimate. So we want to maximize our likelihood. And then if we work in terms of the proportional, this is sufficient because any constant prefactor that just alters the magnitude of our likelihood does not change the position or the arc maximum of our optimization problem, this m. And by the same argument, we can again convert from the likelihood into the log likelihood, since this allows us to perform the optimization a little more easily. So let's look at the log likelihood. And of course, in order to obtain the log likelihood, lowercase l of our data, we're going to apply the logarithm to the likelihood that we have found so far. And then if we apply this logarithm to this term here, then the logarithm is the inverse operation to the exponential. So those two cancel. And then we are essentially getting something that is equal up to an additive constant. That's because we are applying the logarithm to something that was proportional to the likelihood. And this then turns it into equal up to an additive constant. And in that particular case, we will get, so the logarithm cancels with the exponential. So we will get minus 1 over 2 sigma squared times the summation from I0 to capital N minus 1 over yi minus lowercase xi transpose m in brackets squared and then closing brackets. No, we don't need a second closing brackets anymore since the exponential is gone. And here we will again have a prefactor, so 1 over sigma squared, which we can get rid of by again speaking in terms of the proportional. So we will then have something that is proportional and up to an additive constant, and this one is minus 1 over 2, so minus 1/2, and then the summation from I0 to capital N minus 1 over the yi data point minus the xi data point transpose times m in brackets squared. And then as said, we want to perform a maximum likelihood estimate. So let me note that down. This will be an MLE. And then we say that our m star, so the optimal value in terms of the maximum likelihood estimate, is going to be given as the arc maximum over this expression. So it's approximately or proportional and up to an additive constant our log likelihood. So we will apply this arc maximization over this expression, minus 1/2 summation from I0 to capital N minus 1 over yi, or in brackets yi, minus xi transpose m in brackets squared and then closing brackets. And we are optimizing over all m's from a d-dimensional space. So m will be a d-dimensional vector, with d being, for instance, 2 in our case here. And then we will find the 2 entries by performing this arc maximization. And in a similar argument to the one-dimensional case, we can turn this into a minimization by removing this minus sign here. So this is equal to an arc minimization over all m's again from this d-dimensional space. And then we will here have a 1/2 summation I0 to capital N minus 1. And we have our yi minus xi transpose times m in bracket squared, and then a closing bracket again. And this is similar to the one-dimensional case. This is our least squares loss. The difference here in comparison to the 1D case is that we have a scalar product instead of just a multiplication, but so far those are quite similar. However, what we're seeing here is not what I've shown in the intro. So if I go all the way up, I showed you a little bit of a different form. So here we also have a minimization, but then we don't have a summation term. And instead we have this norm structure of vector y minus a matrix x times m. And this is just a more clever way to express that, which also helps us to translate it into a form where we can easily solve it on a computer. And for this, let me go down all the way to our derivation, and then let me introduce to you a data matrix. So let me call this a data matrix, and this will be capital X with a double underscore. And this matrix is a collection of all the data points we have. And we will use a convention in that it is an n by d dimensional matrix. So it will have n rows and d columns. And then inside each of its rows, it's going to have the data entries. So the first row will be entry x0, then we will have entry x1, then we will have entry x2, and I think you get the point. Then by having n rows, we have it from x0, x1, and so on and so forth. Then we also have our parameter vector. So the parameter vector, and this will just be the m vector that you've seen. So m is going to be a d-dimensional vector. So it has d rows in that case. And here we will have an m0 and an m1. And the number of entries here has to match the number of columns, obviously, if that is a d-dimensional vector. And now I also want to collect all the dependent data points that we have, so the y's in one vector. And maybe let's call this the target vector. And here in that particular case, I want to call it capital Y underscore. And maybe it would be a little bit smarter. Maybe let's call it lowercase y underscore in order to match the syntax of scikit-learn. And then let's have a vector here as well. And this vector shall be having n rows or n entries. And there we basically have a y0, we have a y1, we have a y2, and so on and so forth. And here, similar to these entries here have to match those. So in other words, the pair of an x0 and a y1 is what is making up the entry in our scatter plot that we've seen earlier. And now if we look at what we have here, so our loss function is going to be 1/2 summation and then of this expression. So for each entry in our sum, we are performing a scalar product. And the scalar product is taking, for instance, this row and multiplying it with the entire parameter vector, and then it is subtracting this value. And the result of it is going to be squared and then added up. So we can also translate that into a way to use matrix vector products efficiently. So let me first propose that, and then we will look at it in a second. So for this, I want to look at the following operation: vector y, so this target vector that we have, minus matrix x multiplied with vector m. And here we have a matrix vector product. So this one is multiplying this matrix and then right multiplying the parameter vector m. And this will basically perform a product such that the resulting vector out of this is going to have in each of its entries the row multiplied with the column, row multiplied with the column, row multiplied with the column. So in other words, this will be some sort of a prediction that we make. And then by having an element-wise subtraction, this basically refers to the subtraction that we also have here. So the ith data point on the dependent variable is subtracted from this scalar product. So this would yield a vector of entries here. So this would yield this vector here. And so essentially, in order to represent that, let me call that, in order to give that a name real quick, let's call this expression here the t, maybe target function. And then we know that the target function is going to be given as 1/2, and then the summation from I0 to capital N-1. And then we will just take this expression here and view it as a vector in which we index the ith entry and square it, right? So this is kind of the matrix vector operation, and then we're getting out a vector, and then we are taking each entry, square it, and sum it up. And this can also now be represented as an inner product. So what I mean by this, so let me just note it down, and then I think it will become clear. So we will have a 1/2, and then an y minus x times m in brackets transpose times y minus x m. So just this multiplied by itself. And for the sake of this, let me just maybe call this expression, let's call it delta y, because it's the difference between the y, how it should be, and how our linear model it is predicting. So, and this one shall also be delta y, and that's of course a vector. And so basically, if we look at the delta y vector, this one has delta y 0, delta y 1, and so on and so forth. And of course, it has also n rows or n entries. And then by performing this scalar product, we are multiplying row by row. So in essence, we are getting delta y0 multiplied with delta y0, and then plus delta y1 times delta y1. And in essence, we're getting all the entries squared and added up. And this one is identical. And just let me highlight this once again. So here we looked at the entries of the vector element-wise, squared them and summed them up. And this is identical to taking the scalar product, aka inner product, between the delta y vector. And then we can also express this y minus xm in terms of the norm, because the norm or the 2 norm can also be represented by the help of the scalar product. And this one is going to be equal to 1/2 and then the opening for the norm. And inside we will have this delta y vector. So in other words, a y vector minus our data matrix x, and then times the parameter vector m. And we will have the 2 norm, which is equivalent to this inner product squared. And if you still don't believe me that this is an equivalence to the summation term, I just want to derive that from the multivariate normal once again. And for this, we have to also look at a slightly different directed graphical model. So let me call this from the multivariate normal, so MV normal. And here I want to look at the following directed graphical model, where we have an given x, and this time this x is not just a vector or scalar, but here we have our full data matrix. And this data matrix M is then causing our full target vector y. So this will be y vector. And then of course into the y vector, we again have 2 entering arrows. So we will first have our given sigma as a scalar. And then here we have our non-given parameter vector m. And here you now see that y is going to considered as a vector. And the difference was that in our original directed graphical model, we considered y as a scalar. So in that particular case, we could do the likelihood by the IID assumption and just use a univariate normal. But now, since y is a vector itself, we have to use the multivariate form of the normal distribution. So in other words, we can say that the y vector is going to be distributed according to a normal distribution over the y vector, where the mu vector is going to be given as data matrix x times m. I will explain that in a second. And the covariance matrix capital sigma is going to be sigma squared times the identity. So in other words, we will be having an isotropical multivariate normal. So an isotropical multivariate, maybe let's also call it Gaussian, because these two names are equivalent. And since we have a multivariate normal, we also have a high dimensional mu vector. And here you have to be really careful that here the high dimensionality is in terms of n, so the data points. So not in terms of the dimensionality of the input space. So this mu will then also be an n-dimensional vector. And I think this makes sense because X is going to be an n by d-dimensional matrix, and M is a d-dimensional vector. And then if you perform a matrix vector product with n by d times d, you will get an n-dimensional vector. So here you have to be a little bit careful, but we can use that in order to express the probability of y. And this one can then be expressed, so we know the probability of y vector given X matrix, M vector, and, well, covariance matrix. So however you want to phrase it, so maybe let's just call it the sigma here. And this probability will then be, or maybe I'll put it to the next line, will then be 1 over the square root of 2 pi sigma squared in brackets raised to the power n, multiplied with the exponential of minus 1 over 2 sigma squared, and then vector y minus matrix x times parameter vector m in brackets transpose times y minus us. So basically the same expression again. And we would have the inverse covariance matrix here in between. But since the covariance matrix of this isotropical multivariate Gaussian is just in terms of an identity matrix with a prefactor, so we just have one parameter there, we can express it in that particular way. If this sounds a little bit weird to you, then I would advise you to go back to the intro to the multivariate normal and also to the different ways of describing the covariance matrix here. Either way, we now have this expression, and then we can also calculate the likelihood of our data. And in this case, the likelihood of our data is equal to this expression that we have here. So we can just copy it. So the probability of the y vector given the x matrix, the m vector, and the sigma scalar. And this one will then be proportional. So we will again make the idea that this constant prefactor just affects the magnitude. So we can kind of ignore it in that sense. And this one will then be the exponential of minus 1 over 2 sigma squared, and then we have this construction here, target vector m minus data matrix x times parameter vector m transpose, and then the same expression. And you can already see that we don't have a summation or a product anymore. And that is because we moved from a product in terms of this IID assumption to just considering all the data points as the random variable by themselves. And it turns out that this will deliver the identical results, but maybe this is a better motivation for the matrix form. Okay, so this one was the likelihood. Let's also consider the log likelihood. And this log likelihood, as before, will just be, we will apply the logarithm to our likelihood expression, and then we will get something that is equal up to an additive constant. And I will just skip the next line because we will then again use a proportional. So I will just say this will be equal up to an additive constant, and it is also proportional to minus 1/2 of y minus x m transpose y minus x m. And here we can already see this, what we've seen before, that if we have this inner product between these delta x vectors, this is equivalent to having this norm. So it is minus 1/2 and then the norm y minus x m in the Euclidean norm squared. And this in essence will then yield a maximization problem again, and we can swap it to a minimization. So in essence, after the same steps as before, we can find our m estimate as the arc minimum over all m's from this d-dimensional space over the 1/2 and then this norm expression. And I hope that was maybe a second motivation why this matrix form is equivalent to the form of the summation, at least mathematically. However, from a computational point of view, this is way more efficient. And on the other hand, this is a standard problem in linear algebra. So this is a standard problem in linear algebra. And this is also, I mean, I already coined it prior, but it's the linear least squares problem. So linear least squares problem. And it is such a standard problem that you will even find separate algorithm to just solve this problem. And in the example that we're looking at shortly, we will use NumPy. And here we would, for instance, do, so let's say, for example, with NumPy, so you would do the following. You would say NumPy dot linear algebra, so dot linalg dot lstqr for least squares, and this takes then 2 entries. So we need a matrix A and a right hand side B, and this then matches what we have here. So we match the X data matrix with A and the Y target vector with B, and this will then give us, so the result of this is going to be the M star. And what it is doing under the hood is using some form of matrix decomposition to solve this really efficiently. And this is also what I want to highlight here. There is a closed form solution. So there is a closed form solution. We won't be looking at it in this video, so tune in for the next one in order to see how we are able to solve it such efficiently. There are multiple ways actually, but the big advantage is no numerical optimization is needed. So it says no numerical optimization is needed. And why am I emphasizing on that? So this means no gradient descent. So probably this is the typical algorithm you find here. And often if you don't have to use gradient descent, you tend to be faster. And also on top of that, you are more reliable, more accurate, and so on and so forth. And that's something that is an extreme advantage of linear regression. So let's start with a quick example in Python. I chose to use a Jupyter notebook here because then we can embed the 3-dimensional plotly plots more easily. So we need plotly, so let's import plotly.express spx. Then we will need NumPy, so import NumPy as np, and let's run this. And then I want to perform our linear regression on some artificial data. So we will have a reference M vector, which we will be using to create some reference data, which we will also add some noise just to not have it that easy. So for this, I first want to draw some input, some random input. So x equals numpy random.rand, and say I want to have a 60x2 matrix. This is going to be our data input matrix, and we have a 2-dimensional feature space with 60 samples. Let's execute that. And then I want to have a reference M vector. So maybe let's call this mref. And this one is a NumPy array with 0.3 and 0.5. So in other words, our linear function that we in the end want to find shall be having a slope of 0.3 in x0 direction and 0.5 in x1 direction. And then based on that, we can create our reference data y, which is going to be m reference at 0 multiplied with the 0th column of x, so x colon 0 plus m reference at 1 multiplied with x colon 1. Here we go. And then let's look at this data real quick. So let's do px.scatter3d for a 3-dimensional scatter plot, where x is the first column of our data matrix, y is the second column, and z is going to be the y here. Oh, of course, we need an x before brackets. let it run, and then we get our three-dimensional scatter plot. Here we go, and we can swivel it around, and you see all the points are located on one plane. And that's of course because we have drawn the points randomly in XY direction here. So this is x0 and x1. And then the set is given as this linear function. Of course, this would be a little bit too easy. So let's just add some noise. And in accordance to the assumption that we made in the derivations as well, this noise will be in terms of the normal distribution. So let's sample some noise. So let's say noise, it's going to be np.random.randn for normally distributed random numbers. And for those we need 60 because we have 60 samples. And I just want to scale it by 0.1. Shift enter to execute it, and then we're good to go. So then we can create a noisy y, which is going to be y plus noise. Execute it, and then again, let's have a scatter plot. So px scatter 3D on x is again the first column of our data matrix. Y is the second column, or first when you have a zero-based indexing. And z is now going to be the noisy y. And then we have a scatter plot. As here, you can see if we would have a top-down view, maybe something like this, you see those are the identical positions in x, y, or x0, x1 coordinates. But for the z ones, we now have a couple of noise added. So in comparison to before, those are no longer on one plane, but those are a little bit around this plane, so above or below. So this makes it a little harder for linear regression. Well, then we can use the noisy y and the capital X to get an estimate. So let's call this the least square result, which is going to be numpy.linalg.least squares. And here again, this is just such a standard problem that there is one routine in the linear algebra subpackage for it. And here we plug in our X and of course our noisy y, because you're not using the noisy y would be a little bit too easy. So if we were to use the regular y, and then let's also take a look at the result of it. And here's some warning you can ignore for a second. And then this least squares returns a couple of stuff. So it returns one array, another array, an integer, and another array. So this is just like the results of the algorithm they are using under the hood. We are interested in the very first array. So this is our parameter estimate. So let's call this an M estimate. And this is the least squares result indexed at the 0th position of the result tuple. And then we can take a look. Here we have the estimate, and then we have the reference. And of course you see, well, these values are a little bit off, but it's of course because due to the noise, we can't find the perfect fit here. If we had more data, so in the limit of infinite data, including noise, we would approach these values. Of course, under the condition, the data is perfect. So this is of course a reference data scenario. These algorithms tend to not work well if you have outliers or if you have some other weird things in your data, but we will consider this in another video. So far, this works for perfect data. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There are more awesome videos like this. Here you will see now some of them, and I hope to see you in one of the next videos.